Okay, so we discussed about the bit operation and Boolean operation last time, and we are going to start from the next slide today. Okay, so what we have to, the next thing that we have here is to check a specific bit, whether it is 1 or 0. So sometimes you need to check any specific bit in the register to compute compute something, and so we know we might by this time you know how to check the value of a register. But if you like to check any specific bit, how we can do that? So normally you have to design a filter or masking for that. So that's what we are going to see here for next couple of slide, for different sort of different kind of bit checking activities. So here the you can see that we designed a sort of mathematical representation here, how we can check a specific bit. Now k is the number of bit or kth bit that you like to check. So k could be for example 1. That means that you are trying to check the first bit. K value is 2. That means you are trying to check the second bit. So we have two operation here. One, we are going to do a left shift of k number of times. Again, the k is the bit position that you like to check. And then we are going to do a bitwise AND operation with a. A is the value, is a data in which or register for which we like to check a specific bit, means the kth bit here. So let's take a look at an example here. Let's assume that the A is an 8-bit data. So we have a byte, and it has 8 bit here, A0 to A7. And in this example, let's assume that we are trying to check the fifth bit, see that whether it is 1 or 0. So k equals to 5. So let's follow with the example or the mathematical computation that you have to do here. At first, we have to left shift 1 by 5. So if you do that, you can see that we get a 8-bit value representing 0, 0, 1, and there will be 5 lead a trailing 0 here um, for the 1 left shift 5. Now the next operation we are going to do AND, bitwise AND operation with A. So here, let's take a look here. So when you're going to do a AND operation with 0, whatever it is, the value of A0, either it is 0 or 1, it doesn't matter. The result will be always 0. So here, so same for A1, same for A2, same for A3, A4, A6, A7. So all of them will be 0. Now for A5, let's take a look. So our idea is to get the A5 here. So this is the result. That's what we like to do. Let's assume A5 equals to 0. If A5 equals to 0, 0 and 1 will be 0. So we get 0 here. So that exactly is A5. Now, if A5 is 1, 1 and bitwise and 1 will be 1. So we get 1 here. So here you can see that whether it's 0 or 1, by doing this computation, we get exactly the value that we needed here. That means A5. So we get the A5 here. So in this result, you can see that the rest of the bit is basically we made them 0. So we're not interested about them. We're just interested about the 5, A5 here. So that was just copied here. So this is the way that you can check any specific bit. Here is an example of the fifth bit. We checked it out. If you have any question, just feel free to unmute yourself or ask me a question. The second one, we are going to set a bit. So set means in a any specific bit, we like to set one. We like to make it one. Either it is whether it is 0 or 1, whatever it is, we like to set it to 1. So the computation will be like this. Here the field is 1 left shift of k. So we are going to do a left shift of 1 by k times, and then we're going to do an bitwise OR operation here. This could be written also like this format. This is a short format here. So here you can see that normally this is the shortened format, but these are exactly the same. So let's take a look at an example again. We'll see this example with a 8-bit value here. So we have A0 to A7 here. And we are interested to set a bit for the 5th bit, that means A5 here. So whatever the value of the A5, we like to set 1, and rest of the bit will be exactly as it is. So let's take a look. So at first we have done left shift of 1 by k times. So we get this. It's exactly the same that what we have done the last time. Now let's take a look here. What we get in the bit 0. In the bit 0, if A0 equals to 0, so 0 or 0 or operation here will be 0. So we are getting 0 here. If A equals to 1 here, then 1 or 0 will get 1. So meaning is that either A equals to 0 or 1, we get exactly the same value here. If A equals to 0, we get it 0. If A equals to 1, we get it 1 because we are doing an OR operation at 0. So this will be the same for A0 to A4 and A6 to A7. Now for A5, since we are doing a OR operation with 1, whether A5 is 0 or 1, it doesn't matter. The result will be always 1 because you're doing an OR operation with 1. So here you can see the final result will be look like this, in which we were able to set any specific bit, in this case, the bit number 5. Okay. Hope that it is clear. If you have any question, just let me know. Okay, so let's proceed with the next operation, where we are going to clear a specific bit. Clear means, once again, that you like to set it to 0. So the operation could be here. You can see that at first we have to do this filter, which is the same that we have done last two case. One left shift of k number of times. K is the number of bit that you like to clear. But we have to do a NOT operation. We have to do a NOT, and then we are going to do an AND operation with A. A is the data or register that you like to clear in kth location. So let's take a look at the same data here. So A, which is a 8-bit value, and again we like to clear bit number 5. So the result will be like this: A0 to A7. Except A5, rest of them will remain as it is. So you can see that A0 to A4 and A6 to A7 will be remain exactly as it is, but A5 will be 0. Okay, so let's take a look how whether we are able to achieve this or not with this mechanism. So we are going to do a left shift of 1 by k number of times. So here k equals to 5. So we'll get 0, 0, 1, and there'll be 5 trailing 0 here. Okay. And then if we do a not, um, mm, it will be completely like flip. So it will be 1, 1. It was 1 here, it will be 0, and all these zeros will be 1. So this is the not of left shift of 1 by 5 times. So you get this. Now we are going to do the bitwise AND operation. So here you take a look once again. If you do the bitwise AND operation with 1, you'll get exactly what was the input, because if a equals to 0, 0 and 1 will be 0. If a equals to 1, then 1 and 1 will be 1. So we are getting exactly the same what we have here. So if a equals to 0, we'll get it 0 here. If a equals to 1, we'll get 1 here. So this will remain same for A0 to A4 and A6 to A7. For A5, since we are doing an AND operation with 0 here, whatever the value of A5, it doesn't matter, because we are doing an AND operation with 0, it will be 0 here. So you can see that after this operation, we are now able to set, we're now able to clear the bit number 5. So by using this mechanism, you can clear any space, any bit into the into this into the register or data. Okay, so the next one that we are going to see here, a toggle is specific bit. So the meaning of toggle is, if it is 0, then we are going to set it to 1. If it is 1, we are going to make it 0. So that's the meaning of toggle. So the logic, so here you can see that we have A0 to S7, and we are interested to toggle A5. So if you do that toggle, that means if A5 was basically 0, it will be 1, and A5 equals to before the operation. If A5 was 1, then it will be 0. For this, we are going to do a XOR with the same filter. So I think one of the important things that you can observe from here, that the filter is more or less very similar what we have seen so far. So we're going to do a left shift of 1 by k number of times here. And here, if we do that, for example, again with the same example, with the same 8-bit data here, A0 to A7, and k equals to 5. And if you do left shift of 1 5 times, you get this filter. And now we are going to do an XOR operation here. So now the way the XOR works, if any of the input, so if 0 and 1, it will be 1. 1 and 1 will be 0, and 1 and 0 and 0 will be basically 0. So if at most one of the input is 1, then it will be 1, otherwise it will be 0. So let's take a look here. If you do an XOR with A0, let's assume that A0 is equals to 0. If you do a XOR with 0 and 0, you will get 0 here. So A0 was 0, we got a 0 here, that's good. Now if A0 equals to 1, and if you do an XOR with 0, it will be 1. So in this case, you can see that if you do XOR with 0, the information remain exactly the same. So that's what we get here from A0 to A4 and A6 to A7. we have to make sure that they're exactly the same. Now for A5, we like to toggle it. So let's take a look here. If A5 equals to 0 here, and if we do 0 XOR 1, it will become 1. So we were able to achieve half of it, meaning is that when it was 0, we got it 1 here. Now, if we have 1 here, then 1 XOR 1, it will be 0. So in this case, we are able to also make that toggle in both cases. If it is 0 or 1, in both cases, we were able to do the toggle of A5 here by doing the XOR operation with 1. I think this couple of examples that we have seen is clear to everyone, and these are very important, and you might need it in assembly operation. Sometimes you like to check a specific bit or specific flag, and so on. You like to do any bitwise operation. You like to extract any bit. This sort of operation is very handy. Okay. Any questions so far?
I have a question, Professor.
Go ahead, please.
So before we perform the 1 left shift K, is A5 already have that value of 1, or is that 0?
So it could be any. So if the thing that we like to achieve, if A5 equals to 0, then we like to get it 1 here. If A5 equals to 1, then we like to get 0 here. The question is that whether by using this filter can we achieve it, and you have to also make sure the rest of the bit will remain unchanged. You cannot change the rest of the bit. You are just working on A5. So here you can see that the rest of the bit, if you do XOR, I'm pretty sure you are familiar with the XOR operation. If you do XOR for A0 to A4 with 0, we have seen that it will remain exactly the same as A6 to A7. But for A5, let's assume that A5 is 0. I mean, it could be, since it is a bit, there could be only two possibilities, that it could be 1 or it could be 0. If it is 0, then 0 XOR 1 became 1. So that's what we are looking for, because A5 was 0, now it became 1, because remember that we are trying to do that together. Now, if A5 is 1, 1 XOR 1 becomes 0, so it will be 0 here. So we are also able to achieve the other, in this for the second input also. So either if 5 equals to 0 or 1, it doesn't matter. Ultimately, we'll be able to toggle A5 based on this filter. Make sense?
Yes, but for these examples, was A5 already defined with bit 1 before we
No, well, it's not defined. We're just showing that it can take any values. It can take 1, it can be 0.
Okay, thank you.
Okay. Okay, so the next thing that we like to understand is the saturation. Before we discuss about the saturation instructions, so we have two instruction here by which we can do this saturation. Let's try to understand what saturation means. So let's assume that you have a sinusoidal a curve, or you are getting input from a sensor or actuator or something like that, providing you a value with the sinusoidal basically behavior. Now, let's also assume that the data or memory that holding this value, or the register that is holding this value or storing the value initially has 16 bits, and the value could be also signed. So if you have 16-bit sign, then the number, you know that it could be minus 32,768 to plus 32,767. So this is the range of the number in 16 bits. I hope you remember that we have seen a circle of numbers for 5-bit numbers in data representation, where half of the number is positive, half of the number is negative. This is exactly the same, but we have seen for 5-bit, this is right now in the 16-bit setting. Now, let's assume that the data that you are getting at some point, so here you can see that it's starting from 0, okay? And then at some point here, it crosses the boundary. It crosses the maximum number that you can basically represent here. So in this case, what is going to happen? Since it is crossing the boundary of the maximum positive number that you can represent, it's going to enter in the negative number domain. So this will go to the negative number domain, and this is exactly what is going to happen. So suddenly the number will become negative, and it will be just completely flipped. And then when it come back here, the maximum positive number, it come back again here like this. So obviously this is completely error, because I mean, you don't like to see something like this happen, because this data becomes corrupted or completely wrong. Same as here, when it crosses the negative threshold here. So this is the maximum negative value that you can have present. So as soon as it crosses the boundary of minus 32,768 here, now the negative number, it crosses the boundary, it entered the positive number domain, and it happens like this. So again, you get some basically corrupted data here, representation into the register. So it's not a problem of the sensor or actuator, it's a problem of the number of base that we have to represent the data. So what do you like to, I mean, what is the optimal solution here? The optimal solution here is no way we can represent this number, because these are way beyond the capacity of the 16-bit. We have to accept it. There's no way we can do that. So the max optimal solution could be anything above this number, 32,767, will be 32,767. Meaning is that if this any number that crosses here will be maximum number. Any number that is crosses the maximum negative number, the minimum negative number that you can represent will be the minimum negative number that we can represent into the by the 16-bit number system like this. Okay, so it will cut. So this is called saturation. So when it basically spill over the boundary, we are going to make a threshold there. We're going to basically set a maximum number there. Okay. So let's take a look on the two assembly instruction. One is for sign saturation, one is for unsigned saturation number, where, so it is sign saturation. Here is an example here. It says that, for example, since it is a signed number, the number could be represented in n number of bits. If you have, for example, n could be 15, n could be 32, or n could be 10, 11, whatever you like to basically do, define the saturation range. So the number would be, the maximum number that we can represent is 2 to the power n minus 1 minus 1. And the minimum number that you can represent is minus 2 to the power n minus 1. So here, when saturation, this what it is going to do if the number is greater than the maximum number that we can represent into n bit system, which is this is the maximum number that we can represent in a n bit number. If the number crosses this maximum number, it will be 2 to the power n minus 1 minus 1. So this is the maximum number that we can that will be replaced. Any x that will be over this will be replaced by maximum number that could be represented in n bit. Here I can see a mistake here. X less than minus is less than minus 2 to the power n minus 1. If a number is less than the smallest number that we can represent into the n bit, then it will be minus 2 to the power n minus 1. So this will be the value. If anything less than minus 2 to the power n minus 1 will be minus 2 to the power n minus 1. And otherwise, in any other cases, it will be as it is, because there is no saturation will happen only these two cases. So here is an example of this. You can see with the sign saturation, you have like you can define any number of n here. So here the number was defined by 11. Okay, so then this will be 2 to the power 10 to minus 2 to the power 10 to plus 2 to the power 10. So that's basically the range, saturation rate. For unsigned saturation, obviously here you can see there is no negative number, there's only positive number. So we can specify more numbers here. So and it starts from 0. So the maximum number in n bit we can represent is 2 to the power n minus 1. So it's not 2 to the power n minus 1 here, 2 to the power n. So because the number start from 0. Okay. So if any number that is greater than 2 to the power n minus 1 will be replaced by 2 to the power n minus 1. Otherwise, it will be 0. So the instruction for this is unsigned saturation user, and by which you can basically define an output range, and anything beyond this range will be replaced by 2 to the power n minus 1, this value. So I think the next couple of examples that we are going to take a look is by how can we do the bit and byte order reversal. Sometimes we need this operation to do bit manipulation. So we're going to take a look. The first one is R reverse bit. So we're going to do reverse bit order in a word. This is, if you understand the C program, this is the mathematical, not mathematical, this is the programming representation of R bit, which what it is doing, if you read it here, we can also see it in the graphical representation. So Rn will be the source and Rd is the destination. So in the source, whatever the bit 0 was, it will become like bit 31. And whatever the value in the bit 1, it will be bit 30th. And whatever the bit 31st, it will be bit 0. And whatever is bit 30th, it will be the second bit. So here you can see that the least significant bit will become most significant bit, and so on. And the most significant bit will become the least significant bit. So here is an example of the R bit. So for example, if you, because it's in a hex representation, it might not be so easy to understand here, because you're doing the reversal in the bitwise, but if you run this operation, you'll see exactly the same value here. So let's assume that we are storing R0 equals to hex 1, 2, 3, 4, 5, 6, 7, 8. And then we are going to do R bit, reverse bit of R0, and we're going to store the result in R1. If you do that, you'll find it out that we get a complete bit wise reversal of R0, and that result is stored in R1. It's not so, since it is a hex representation, it's not so easy, but I hope everybody understand the philosophy, how our methodology, how it is done. So next one will be a bit easier to explain with the example. The next one will be the rev, reverse byte order in a word. So if you think about a word which is byte 0, byte 1, byte 2, and byte 3, rather than doing the bitwise reversal, we are going to do byte-wise reversal, meaning is that the bytes 0 of the source will become the byte 3 of the destination. Byte 1 of the source will become byte 3 of the destination. Similarly, byte 3 of the source will become byte 0 for the destination. So if you can take a look, here is an example, LDR R0, and let's assume that we have put the same value here, 1, 2, 3, 4, 5, 6, 7, 8. Now, if you do byte-wise, obviously this is the byte 3, byte 2, byte 1, and byte 0. So this is a byte 0. So this will become byte 3, and which we see it here. And byte 1, which is 56, become byte 2. And the most significant byte, which is here 1, 2, byte 3 becomes byte 0. You can see it here. So it's easy to, so here, this is pretty much obvious to see that with the rev, you can revise byte in a word. So you have to reverse, if you have to reverse in half word boundary, then you have to use rev 16. So in the rev 16, what we are doing, we're doing the byte reversal, but the reversal is done by half word boundary. It means that the byte 0 will come to the location of byte 1, byte 1 will come to the location of byte 0, byte 2 will go to the byte 3 location, and byte 3 will come to the byte location 2. So if you take a look in the, if you just divide it in half, and the reversal is going on in half byte, half word boundary. So here is an example with the same value, R0, 1, 2, 3, 4, 5, 6, 7, 8. And you have to divide it in the middle because it's F16. So 1, 2, 3, 4 is the upper half word. 5, 6, 7, 8 is lower half word. So then we are going to do the byte reversal. Then it will be 3, 4, 1, 2. Okay. The upper half will be reversed like this, and the lower half will be reversed like 7, 8, 5, 6. So this will be the value that you'll get after the reversal. Now let's take a look the another example here, which is reverse byte order in bottom half and sign extended. So in this example, what we see here, that the upper byte, the upper half word, that means byte 2 and byte 3, is completely ignored. So we are going to completely dump this 2 and 3, but the byte 0 and byte 1 will be reversed in the byte order. So byte 0 will become byte 1 will become byte 0. But the interesting thing is here is it will be sign extended. So what is the meaning of the sign extension? It means the in the boundary. So after the reversal, this is the boundary maximum, the most significant bit here. So meaning is that the 15 bit of this half word, whether it is 0 or 1, if it is 0, then it will be a 15 bit to 31st, 16 bit to 31st bit, it will be 0. So you can see that the sign is we are extending the sign. If it is 1 here, if we get 1 here, then 1, all these 16 bits here will be 1. So this is called sign extension. So most significant bit here will be extended as a sign, whether it is 1 or 0 here. So let's take a look at the same example here. This one is a bit different, but let's assume R0 equals to a value is 33448899, and obviously it's in hex. So if we do R rev sh R0, R1 R0, so we are doing the reverse byte order in bottom half word and sign extended of R0. So first of all, the top half word will be completely ignored. So we are going to ignore 3344. So this will be completely ignored. And the lower half, here you can see that 8899 will be reversed. So reversal will be done in byte order. That means 88 will be the lowest byte here, and 99 will be the upper byte here. Okay, so now what is the most significant bit of 9? So 9, if you take a look, the most significant bit here, 9 is 1. So that's the reason why the 1 is extended for all these 16 bits. So all the 16 bit will be replaced by consecutive or sequence of 1. So that's why it becomes F, 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 F here. So why do we need this kind of sign or 0 extension? The reason is that let's take a look at an example of it, and I think it will be clear to everyone. So let's assume that you have a 8-bit data and you have a 16-bit and 32-bit data. So in 8-bit data, you have A equals 2 minus 1. And in the 8-bit, A, if you represent the minus 1, it will be FF because it's an 8-bit. If you represent minus 2 in 16-bit, I'm pretty sure you know it will be FFFE. So that will be the minus 2 representation in 16-bit. Now let's do that. C equals to, at first, C is a 32-bit data. Okay, so C equals to 32-bit data. Now what we do it here, we copy A, which is FF, to C. So if C is a 32-bit data, here is like 8-bit data. So what is going to happen? The 3 upper byte, because C has 4 byte and A has 1 byte. So obviously this byte, this will be copied to the lower byte, which is byte number 0, and byte 1, byte 2, and byte 3 will be, let's assume that if you don't this sign extension, it will be 0. So what is going to happen? Suddenly, you the -1 becomes 255, because it is, if you have it like in unsigned, if it is unsigned, if it is all of them is 1, then it is 255. So when you copy it, if you don't do the sign extension here from 8-bit to 32-bit here, when you're copying here, suddenly -1 become plus 255. So that's not what you like to see. So that's why when you're copying the data from smaller place to the bigger data memory or register, you have to make sure that you extend the sign so that -1 become the -1 when it is copied to the 32-bit value. So that's what we have here. If it is sign extended, then FF, the most significant bit is here is 1. So if you extend it, then you see that you get all of them is FF. This is the also -1 representation in 32-bit. Same as here, when you are copying the -2, which is FFFE, into 16-bit to the 32-bit. If you don't do the sign extension, the lower 16-bit will be this FFFE, but the higher 16-bit will be all 0. So once again, suddenly a negative number becomes a very big positive number here. So that's why we need to also do the sign extension here. If we do the sign extension, then -2 in the 16-bit will remain -2 into the 32-bit. So this is something you should pay attention when you are copying a sign number from one memory location to the another, and in cases, especially when you are copying from a 8-bit a byte to a basically a half word or a 32-bit register, you have to make sure that you do the sign extension. Otherwise, you'll get basically the wrong result. Okay, so here zero and sign, for zero and sign extension, there are a couple of instruction here. So here you can see that you can do S sign extension for extend a byte. So for example, here by SXTV, you take 1 byte and then from a specific memory or register, and then you do the sign extension. So here, let's assume that LDR, you're loading R0 with FFAA8765. If you do sign extension of you're just taking 65, you're just taking 1 byte here, 65, and then you're doing the sign extension. And as you know, that's 6 in a binary representation of 6. The most significant bit will be 0, so that will be extended, and that's why R1 will become 65 at the byte 0, and rest of them will be 0. And in another example of here, and this instruction is XTH, which is sign extended half word. So if you like to extend the half word, so here, if you take the half word of this value, that means you're going to take 8765. So that's we have taken. Now, since 8, we are doing the sign extension, so 8 has 1 in the most significant bit, so that one will be extended. So that's why you can see F, 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 F here. So the sign has been extended here. You can also do UXTV, which does the 0 extended a byte, meaning is that it is going to copy a byte, it is going to ignore the sign. So for example, UXTV, you see that we are taking the only one byte, 665 here, and then we are ignoring the sign here. So if it is, for example, here is 8, still it will be 85 here. It will be not 85 and all FF here, because you are doing the unsigned or 0 extended a byte. And 0 extend half word, the same thing, you are going to take the lower half word, but you're not going to extend the sign. So by using UXTH, unsigned extension of the half word, here you can see that you are taking the half word 8765, this is the lower half word. Although the most significant bit is 1, but you are not extending it because you are intentionally using unsigned half word extension here. So yeah, you assume that you like to take this um, as a basically 0 extended number, not the sign extended number. I hope this discussion clear to everyone. If you need to copy value from one location to the another, please make sure that you understand that whether it will be signed or unsigned, and use the appropriate instruction to copy so that you can either 0 sign extended or 0 extended to make sure that you get the appropriate result.
Hi, Professor. Can you explain the first one? SX, TV, R1, R0?
Yeah. So R0 equals to, we have 55AA8765. So the SXTV is going to do sign extend a byte, meaning is that it's going to copy the lower byte of R0 to R1, and the lower byte is 65 here, so it copied the 65 into R1. Now it's going to do the sign extension. So sign extension, for the sign extension, it will take a look the most significant bit here of 6. So the most significant bit of 6 is 0. So since the most significant bit of 6 is 0, then it is going to extend rest of the 3 byte as 0. So that's what you see here, it extended as a 0. Let's assume if it is here is 8, for example, if it is 85 here, and for the same instruction, it will be 85 here, and rest of them will be F, 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 because 8 has the most significant bit 1, so that 1 will be extended all over for the next 3 byte, and that's why they will become FF here. Is it clear?
Yes, thank you, Professor.
Welcome. Okay, so next we are going to discuss about the data movement operation. There are several of them, and we are going to use the most frequently one is that you use is move. This is used, the move operation is used to move the data from one register to the another register. So this is normally done is only for the register. You cannot use the move operation to move the data from the memory and the between the memory or memory to the register. Everyone, I think, by this time is familiar with this concept. So move is used to move the data from one location to the one memory location, one register to the another register. So here, for example, we are moving the data from R5 to R4. You might have not seen MBN, which is another a variant of move. Before it moves to R5 to Rn, it's going to do a NOT operation. So meaning is that it is going to flip every bit here, and then it's going to copy the data to R4. So it's a not of operand 2, and then it moved to the R4.
Professor, I have a
Yes.
question about MOV. So when it only copies, but it doesn't store it in the register, right? Or it does?
Yeah, it's so for example, move R4, R5. The meaning is that it's copying the data from R5 to R4, and whatever is in R4, it will be erased, and it will have the new value will be R5.
Okay, thank you. Thank you.
Welcome. So and then we have MRS. We hardly use it. So this is instruction is used for move from a special register to the general register. So what is the special register? Like for example, PC, SP. So for this, normally you don't like to do it in this way. You like to use MRS. So MRS is used to copy a special register to the general register. So here you can see that you're copying application program status register to the R0. The other instruction is other way around, which is moving from the general register to the special register. So here you can see that you are moving data from the R0 to the APSR. So you're copying the data from R0 to the application program status register with the MSR. Normally, I mean, we don't use this very frequently because this special register, it's better you don't basically, you know, I mean, we don't need them to change because the stack pointer and program counter, it's controlled by the microprocessor. If you need to check the flag, there is a way to check the flag. We normally don't copy the flag to a register, but it in some application you might need to. So that's why the Cortex M4 architecture came up with these instructions. So these are the instructions available for you to move data from the special register or move data from the general register to the special register. Okay, I hope this I hope this discussion is clear. And if you have any question, please let me know. Otherwise, at this moment, I would like to take a short break for 10 minutes. And we'll come back at 3:10. Okay, so we're going to start from where we left off. So the next thing that we are going to discuss about is barrel shifter. The barrel shifter is a hardware that is attached to the ALU, because the ALU operation that we are trying to take a look right now. If you take a look in the Cortex M4 architecture, so this is, if very inside of this processor, we can see that there is a barrel shifter that is attached with the second operand. So it is not with the first operand, but with the second operand is a barrel shifter. So the purpose of the barrel shifter is to do many shifting operations like left shift, right shift, rotation, and so on. What is the benefit of having a barrel shifter with the ALU? So let's take a look on an example of it. There is an example in the previous slide. I didn't explain it because we're going to explain it here. So here you can see that we have an add operation, which is an ALU operation, and we are doing R0 plus R0, and you are storing the result in R1. So your the operand 1 will be R0, operand 2 will be R0, and the result will be stored in R1. But you're also adding LSL, that means logical shift left, number 3. So what you were saying here, before it get added into ALU, you like to shift the second input, which is R0, by 3 times, and then you pass the value to the ALU to add it to the operand 1. So if you take a look here, if you do left shift of R0 3 times, if you do left shifting of R0 1, which means it is multiplied by 2. So if you do shift 1 time left shifting, it becomes 2R0. If you do another time left shifting, so 2R0 will become 4R0. If you do another time shift left, then 4R0 will become 8R0. So ultimately, what it will become, that you have, by shifting 3 times, the R0 here becomes 8R0 plus the R0, so you get ultimately 9R0. So you could achieve the same result by doing a multiplication. Meaning is that you can multiply R0 by 9, and you get the same result. So what is the benefit of doing it in this way? What is the meaning of adding a barrel shifter with the processor? I mean, if you add this shifter, obviously you have to implement it hardware, so you need to sacrifice some silicon space for this barrel shifter. Now here is the benefit. The multiplication hardware has higher latency than the ALU. Let's assume that the ALU execute an instruction in 1 clock cycle, and the multiplication hardware, which is different hardware, it takes at least, let's assume for in general case, it takes around 3 clock cycles. So it's 3 times more time consuming. So by adding a barrel shifter here, if you can formulate the multiplication, the simple one, obviously the complex one you cannot do it here, but the simple one, simple multiplication, you can bypass the multiplication hardware. You can use the barrel shifter to do this kind of multiplication here that we have seen here, that we're multiplying by 9, but actually we're shifting 3 times and adding it to the R0, get exactly the same result. So rather than spending 3 clock cycle, we can complete it by 1 clock cycle here. So your program becomes like 3 times faster. So this is the reason why they have added a barrel shifter in the second operand, and we are going to take a look of more details about the barrel shifter in coming slide. I think the philosophy why they have put a barrel shifter should be clear to everyone to make. So the second operand of ALU has a special hardware, and that is called barrel shifter, and that helps to basically help to run or execute instruction that could be otherwise run in the multiplier. So that makes it faster. So what are the instructions that we have here? That is barrel shifter that we have available. This is an example here. For example, we have logical shift left. So the way the logical shift left works, the most significant bit will spill to the carry, and the 30 bit will become 30 fast, and bit 0 will become bit 1. And obviously here you can see that we'll have a void here at V0 at the bit number 0. So we have to do a padding of 0. So 0 will be padded here, and we'll get a spill at bit 31, and which will be stored in carry. Logical shift right, which will be exactly opposite. So bit 31st will become bit 30, and so on. Bit 1 will become bit 0, and obviously there will be spill from the right hand side here, and bit 0 will go to the carry, and there will be a void here because you are shifting to the right, so we have to add a 0 here. Rotate right extended. These are the assembly instruction that you have to put with the ALU operation that a bit earlier we saw. So for example, here here we saw that we put LSL here. You can put other instructions like LSR, RRX, ASR, and ROR also. So rotate right extended, it's works like this way. It is a rotation. So, but in the rotation, we have also the carry flag in the loop. So bit 0 will go to the carry flag. Carry flag will becomes the 31st bit, and 31st bit will become the 30th bit because we are doing the rotate right. Arithmetic shift right is going to happen in this way. So bit obviously this will be shift right, so everything will be shifted towards the right. But in the two ends, in bit 0 it will be spilled and it will go to the C, and bit 31st will be in bit 30, but also it will be copied to the same location, meaning is that it will remain unchanged here. And the rotate right will work in this way. It is a rotation, so to the right, and here you can see that the bit 0, which was spilled over here, it will be not only stored in carry, but it also will be added on bit 31. So you may ask that why there is rotate right but no rotate left. Rotate left can be replaced by a rotate right with a different rotation offset. So we can so because every operation here will require some hardware, so they have you can achieve rotate left by using a rotate right operation with a specific offset. So with that, we are going to see an implementation of a barrel shifter. This course is not designed to go to the to take a look on the hardware implementation of the processor. So if you like to design a processor like even 8-bit microprocessor and so on, you might think about it in 400D and so on. And there you can design a processor with you know, I mean, kind of all the expertise that you have here, you got so far. So this course, we are mostly understanding the processor architecture and also understanding how it works by understanding the assembly programming. But there's an exception here. We are going to take a look of, in this section, a very simple implementation of the barrel shifter. We're going to take a look on barrel shifter for the rotate right. So a bit earlier you saw that there are many, like 5 or 6 instructions that are implemented inside the barrel shifter. every instruction require a circuitry, a set of circuitry need to be added to the processor to make sure that operation works. So the circuitry that you are going to see right now is a logical, circuitry, a logical implementation of the barrel shifter only for rotate right. So we are going to see only for the hardware for the rotate right. And the rotate right, original rotate right is a 32 bit in barrel shifter. But for simplicity, we are just taking we're looking here a 4-bit barrel shifter. So the barrel shifter that we have here only works for 4-bit, and the hardware that we are going to see right now, or you see at this point, it's only for the rotate right. So let's take a look. So here is the input. So D0 to D3 is our 4 input, D0, D1, D2, and D3. And Y0 to Y3 is our output here. And here you can see this barrel shifter is implemented by using an array of 2-in-1 multiplexer. So here you can see that the basic unit of circuitry is a multiplexer for this barrel shifter. And here you can see that it has 2 input, and it allowed to pass only 1 output. Now, which output will be selected? It's based on a switching basically input here we have to give. So if the switching input is 0, then it is going to select the input 0. If it is switching input as here is 1, then it's going to select the input number 1, or the second input here. So it is the input number 0, the first input, and input 1 here is the second input. So if you put 0 here in the switch, it is going to select this one. If you put 1, then it's going to select this one. Since it's so we have cascading multiplexer here. So 2 layer of multiplexer we have here, and there is a specific, you can see there are some connection here. Why this connection was basically like this, the connection means the wiring look like this. We are going to basically take a look right now and see that whether this wiring is the good one for the rotate right in 4-bit. And also here you see that the switching input is at the bottom one is S0, and the upper one is S1. And so the output will be Y0 to Y3. Now let's take a look. If we like to do a rotate right 0 0, if 0 0 means here the S1, which is the top layer of multiplexer. So what also you can see, all the top layer takes the same switching input. So all of them is S1. The bottom layer also take the same basically input, which is S0. So when we are providing the input of 0 0 in the S0 and S1, we are saying that rotate right 0 times. When we are saying 0 1, that means we are rotating one time rotate right. When we are doing 1 0, that means 2 times of rotate right, and 1 1 means the 3 times of rotate right. So here you can see that if you do 0 times of rotate right, the output will be exactly like input. So output will be D0, D1, D2, D3. That's the basically input also. So input and output will be exactly the same because we have 0 times of rotate right. Now, if we do 1 time of rotate right, then obviously the D1, which is the second input, becomes the first input, and the third input, rotate right, it will come to here in the second, and the fourth becomes the third, and obviously the first one will go, because it's a rotation to the right, it will go to D3, the fourth location. So this will become here. So if we do 2 times of the rotate right, then you see here, so you get 1 time of rotate right like this. If you do another time, so it becomes D2 comes here, D3 comes here, D0 comes here, and obviously D1 come in this location. So this is the 2 time of the rotate right of the input, D0, D1, D2, D3. If you do 2 times, it will become like this. If we do 3 times, if you do the math here, here you can see that if you do 2 times, 1 time rotate right, 1 time, 2 time, and 3 time, you see here D3 will come in this location, and so on. So let's take a look. So I hope you understand that how with this, the input becoming output, but we have not seen how really it is done by using this circuitry. So that's what we're going to take a look right now. So let's assume that our input for S0 and S1, the switching input is 0, 0. So both of them are 0, and the input is D0, D1, D2, D3. So if it is both of them 0, and let's see that what you get for D0. Okay, so here, if it is the 0 here, so we are going to select the input number 0 here. So that means that D0 will come here as an output. So, and here also we are going to select the 0 input, because as 0 here is 0. So we are going to select the this input, and the output will be D0. And the same one here for D1. So here you can see that D1 will be selected from this multiplexer, and that will be the output of this multiplexer. And then it's also this D1 coming here as the input, the first input of the second multiplexer. And also we have S0 equals to 0, meaning is that this input will be selected and the output will be D1. Same as D2, same as D3. So here you can see, by using 0 and 0 as an input, we were able to get exactly the result that we are expecting. We got D0 here, D1 here, D2 here, and D3 here. Okay, so that's simple. So let's try to take a look a bit the next one. So 1 time of rotate right. So here again, exactly the same input, D0, D1, D2, D3, but switching input is different. So in the lower level, you can see that which is S0 will be 1. So all this input will be 1, and the upper level will be 0. So upper level. So if you have the upper level is 0, a bit earlier we saw that it is going to select D1, D2, D3, D4. So the input is the output of this will be exactly as the input bits. So D0, D1, D2, and D3. But here, the fact is that you see, we are selecting the second input, not the first input. So here, second input is coming from the second multiplexer. So we're not selecting D0, we are selecting D1 here. So the D1 comes here. So Y0 now will be D1, because we are selecting. So you see that in this multiplexer, there is 2 input coming. One is D0 is coming here, and another is D1 coming here. But since S0 is 1, we are not going to select D0, we're going to select D1. So the output of Y0 will be D1. And here, again, we are selecting the 2, that is a 2 input and in the 0, and this input will be D1, and this input will be D2, and we are selecting D1, D2 here. So it's going to come from the previous stage of multiplexer. So we'll get D2 here, same as here D3. For D3, you can see that it is coming from the D0. So it comes from the D0, and we are selecting 1 here. So that will be the output here. So that looks good to everyone. So any questions so far? Okay. So let's take a look in the 1, 0. So meaning is that we are doing 2 times of shifting. If you do the 2 times of right shifting, then in here we need to make sure that we get D0. And now the control input, the switching input is the S0, which is the bottom layer here will be 0. So it will be selecting the input 1. And the upper layer, S1, will have the input of switching input is 1. So meaning is that S1 equals to 1, we are going to select the second input. Now let's take a look here in the first stage here. Since we are selecting the second input, we're not passing D0, we are basically getting D2 here. So we are getting the D2, and then D2 will be passed here, and S0 will be selecting the first input, so that means we'll have D2 that will be passed here. That's exactly what we are looking here. In the second case, let's take a look in the upper stage here. It's S1 equals to 1, and it's going to give us D3. So it's going to select the D3, and D3 will be passed here, and S0 equals to 0. So it is going to select the first input, which is D3, and D3 will be passed here. And that's exactly what we are looking for as a output of this second bit. And if you take a look on the third one, here, let's take a look here. We are selecting the input of D0, and that is passed here. That's what we are looking for. So here you can see that by just setting 1 and 0 in this circuit, we were able to do exactly the 2 times of shift right. So now if you like to do 1 and 1, which is basically 3 times of shift right, rotate right, and we like to get D3 here. So let's see that we can get the D3 in this location. And in this case, the both S0 and S1 will be 1. So meaning is that in both cases, in both stages, we're going to select the second input. So if you take a look on the second input here, the second input is coming as D2. So D2 is coming here. And in the second input here, so will be D3. The second input here will be D0, and second input here will be D1. So that's what will be the output from all this. Now, in this next one, in the next layer, in the Y0, you see that we're not selecting input from here. We are selecting the input from this layer and this multiplexer, and which is coming from D3. So you can see that it's coming from D3 and ultimately pass it here. And that's exactly what we're looking for here. And here also, you can see that the we are selecting the second input for this multiplexer, and which is coming also from the second input of this multiplexer, which is D0. That's what we are looking for here. And for the third stage, third bit, we're looking for this second input. And the second input is also, we're also looking the second input for this one, which is D1. So D1 will be passed here. and that's exactly what we're looking for. So here you can see that. So this circuit is good enough for 4-bit rotate right when you like to do only 3 times of shift rotate right. Now in reality, that's the, now you see that how complex it will be. In reality, you are not don't like to design a hardware only do like 3 times of rotate right. You like to do like 8 times or something like that, at least 8-bit rotation. That means you can do up to 256 times left shifting and so on. So if you like to do 256 times, then you can see that how many control you'll have. You'll have basically for example, for each of the stages, so you'll have 8 different stages here. So even for the 4-bit, you'll have 8 different stages. And if you think about the 32-bit, normally the register 32-bit, so you'll have a 32-bit basically input with 8 different stages of multiplier. It becomes already too, I mean, busy for us to think in the in our to think about, to ponder about it. It becomes so complex. But I hope the implementation, the hardware, the simple implementation of the barrel shifter with just 2-bit of switching, that means we can do 3 times of rotate right, is clear to everyone. That give you an understanding how the processor is implemented by using the basic blocks. Like here the basic block of this implementation is a multiplexer. Any questions so far? Okay. If it is not, let's go and take a look. You can see that here we can do barrel shifter operation. I think we explained the first one, that you are adding and you are rotating the left, the second operator left shifting 3 times. As you know, the left shifting means multiplication by 2. If you do right shift, that means the division by 2. So here you are shifting 3 times, and it's basically division by 8. If you do arithmetic shift right, basically also a division, but is a sign division. So here I think we discussed about earlier the use of barrel shifter to speed up applications. So if you think that you are looking for a multiplication operation, but this multiplication operation could be implemented by using a barrel shifter here, as we discussed, you should do that, because that will speed up your operation inside the assembly. That's why we're doing the assembly programming, to speed up, to get the maximum speed out of the hardware that we have. So that's so here you can see that if you do multiplication of 9, you can do with the barrel shifter here, and you also can do it by a multiplier, which will require at least 3 times more computation time, 3 times more latency compared to the barrel shifter. So if you like to do a multiplication, you already know how to do it. But today we have discussed how it could be done also with the barrel shifter. With that, we come to the last slide of this chapter 4. We are going to see a set of data comparison instructions. These are also part of the ALU. So the first operation that we are going to use most frequently in the coming days, when we are going to implement the loops, different type of loops, that loops branches that we are going to implement, and that are the integral part of the procedure, that also integral part of the switch and if then else, and also for the loop. So compare is a very important instruction. So the way compare works, it is special subtraction. So it's compare Rn and operand 2. It's going to do a subtraction of Rn minus operand 2, but it's not going to store the result anywhere. You see that the result is not stored anywhere. But using the result, it's going to set the 4 flag, the application program status registers flags, so N, G, C, B. So these are the 4 flags that it is going to update. So the only purpose of the CMP is to update this flag after computing the subtraction. So after computing the subtraction, it uses the result to set this 4 flag. That's basically only the purpose of the comparison CMP, and we use these 4 flags later on to decide whether the number is smaller or greater. What kind of comparison we need to do. We'll see afterwards. We'll see later in this course. CMN, compare negative, it does, rather than subtraction, it add these 2 operand, and using the result, it modify the N negative flag, 0 flag, carry flag, and overflow flag. So these are the 4 flags. I don't think that we use this instruction that much, but just showing here there is existence of this instruction. TST and TQE also some instruction that you can get the same functionality by CMP, but if you need, if you see that there is a need of specific functionality of this, you can use it. So let's take a look. TST, which is test, it does AND operation between the 2 operand, and then set only the negative flag and the 0 flag. So there's only 2 flag it sets based on the result of the AND operation. And TEQ, which does test equivalence, which also which does the XOR operation between the operand 1 and operand 2, and then set the flag, only the 2 flag, N and C. So this does test equivalence. As I said, that the only operation that we are going to use most frequently is CMP, and that does a subtraction Rn minus operand 2 and set use the result to set these 4 flags. Okay, so I think we are done with this ALU arithmetic and logic instructions. So most of the, not most of the, I think good number of instructions we have seen in these 2 lectures. We have seen they are, kind of how they're used, and also we have seen a part of the implementation of the ALU unit, which is a barrel shifter. So this will give you a good idea of the instruction that are available that come with the ALU toolbox and part of its implementation. With that, I'd like to stop here. Is there any question about so far what you have discussed?